On the left, this is what we have been doing, polynomials. And notice the x appears in the base. However, in this chapter, we're going to be looking at these functions where the variable is up in the exponent, and that's where it gets its name, exponential functions. And so let me show you some things that are exponential functions. Notice the base is a regular sort of number, but the variable is up in the exponent. Now here are some things that are not exponential functions. Let's see why. This first one, the base is the variable. That's not what exponential functions are. Exponential functions have the variable in the exponent. This one has variable in both the base and the exponent. And again, the exponential function has to have a constant on the base. This one has a constant on the base, but if you look carefully, 1 raised to any power is always a 1. So this is not actually a function at all. It's just the number 1. Here, however, the -2 is in the base, and x is the exponent. This is not an exponential function because you cannot have a negative number for the base. We want to graph the function 2 to the x, but we want to use the dots to do that. And so let's dream up some numbers for x. We'll start with a 1, plug a 1 into the function, and we get 2 to the first power, which is 2, and the dot at 1, 2. Use a 2 for x. 2 to the 2 would be 4, and so we got a dot at 2, 4. 3 for x would give us 2 to the third power, and 2 to the third power is 8, and so 3, 8 would be the dot. Let's use 0 for x. Now you might remember this from beginning algebra. Anything raised to the 0 power is defined to be a 1. And so 2 to the 0 would be a 1. There would be a dot at 0, 1 on our graph. For negative numbers, in case you haven't seen this before, a negative number means that you're dealing with a fraction. And so 2 to the -1 power is the same as 1 over 2 to the +1 power. The fraction 1 over 2. So the point -1, 1/2 would be here. Choose a -2 for x, and 2 to the -2 power would be 1 over 4. And so there's the dot. -3 to the -3 power would be 1 over 8. So there would be the dot. Now if we connect these with a nice smooth line, the graph would look like this. Now some key features of this graph are this. Always crosses the y-axis at 1. The y-intercept is 1. On the right goes up forever and continues going up forever. On the left of the y-axis, the graph goes down but never touches the x-axis. The x-axis is called an asymptote. That literally means the graph never touches it. And so let's take a look at how we would go about typing this if we wanted to draw the graph on our calculator. The exponent character is how we would type 2 raised to the x power. And so the graph would look like this. Crosses the y-axis at 1, up to the right, down to the left, never touching the y-axis, the x-axis. Let me show you some different numbers instead of the 2. The red is the graph of y equals 2 to the x. The blue would be 3 to the x. The green would be 5 to the x. Here's 1.5 to the x in orange, and 1.2 to the x in purple. Notice they all cross the y-axis at 1. They all go up to the right. They all go down to the left, but never touching the x-axis. Here's the graph of 2 to the x. Let me go through the 3 transformations that you learned back in chapter 2. If we substitute an x minus 3 where the x was, The minus 3 tells us that the graph is shifted. To the right, 3 units. The blue dashed line is the original graph, and the red is the graph of 2 with an exponent of x minus 3. Notice the asymptote here in green stays the same. 2 to the x with a minus 3 at the end shifts the graph down 3. Notice how the asymptote has shifted down. 2 with an exponent of negative x, when you replace the x with negative x, the graph flips horizontally. And a negative on the front of 2 to the x flips the graph vertically. Multiplying x by a small number makes the graph bigger in the x direction, and multiplying by a bigger number compresses the graph in the x direction. Multiplying out front by a small number shrinks the graph in the y direction, and multiplying by a larger number stretches the graph in the y direction. And so those are the transformations. Here are the functions 2 to the x and 3 to the x. There is a special number between 2 and 3, approximately 2.72, whose graph would be in between the red and the blue lines. So the purple graph here is the graph of 2.72 to the x. Now this number is so common in math that it has its own special name and symbol. The 2.72, or more appropriately 2.71828, etc., is a special number called the natural base, and we call it by the lowercase letter e. And so we will see graphs that involve the e. We have the key on our calculator. I'll show you that in a minute. This is an irrational number. Rounded to 2 decimal places, it would look like this. But just like with the number pi, the number e goes on and on and on. It is a non-ending, non-repeating decimal. That's what the word irrational means. You don't have to know all the digits of this. Your key on your calculator is sufficient. And here's where the e is on your calculator. You can type that, press enter, and you'll see 2.71828, etc. There's another key over on the left-hand side that likewise has an e, but has a little x up there. You use that key if you want to raise e to a power. Now finally, I wanted to go through a problem like on the homework involving the dropping of a ball. And so this is what the homework problem looks like. We have a ball, and we're going to drop the ball from 6 feet, and we're going to be told that the ball bounces half its height on each bounce. And so I want to go through with you the scenario. We drop the ball from 6 feet. It bounces back up to 3 feet. That's half of 6. So its new height is 1/2 of what it started. That's what bouncing 1/2 of the height means. Well, on the second bounce, it's going to go half of this. Now watch how I write that. Half of 6 would be 1/2 times 1/2 times 6. And that comes out to be 1.5. Third bounce would be half of that. That would be 1/2 times 1/2 times 1/2 times 6. Now there's a pattern going on here. You notice that each bounce is half of the previous one. So if I take the 6 where it started and half of that and then half of that and then half of that, the next one would be half of what you see there. Now a short way of writing that would be to say 1/2 to the 4th power. And the fifth one would be 1/2 to the fifth power, and so on. And so notice that the 1/2, representing how high it bounces on each bounce, is simply raised to a power. Now this can be written generically as a 6 times 1/2 to the n, where n represents the number of bounces. And so let's write this in formula fashion. If it starts at A, then the first bounce would be half of A, second bounce, half of A times half of A, and so on. And notice again, the 1/2s just have an exponent. So this is the formula that we will need for the bouncing problem.